Merry Christmas, everybody.
Isaac Newton was born on Christmas Day. When he was 24-year-old, 1665, as he was sitting under an apple tree, observed an apple fall from above. With the fall of an apple, Newton came up with a simple equation that connected the earth to the heavens. F is equal to g m1 m2 over r squared.
My left hand and my right hand, they were being pulled together. Me and the earth, they were also being pulled together, which is what prevents me from propelling myself all the way into space when I jump. This is the universal theory of gravity.
A few decades later, John Michell, another English clergyman, on the Christmas day discovered something big.
Mitchell had a simple idea. What if you had a cannonball on the top of the earth, and that cannonball shot up a cannon at 90 degrees?
The cannonball will go up and up, however, the gravitational pull will bring it back to the earth. Now, John Michell was thinking, what if I double the velocity? Then the cannonball will go up, 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 keeping the same angle. It will go
4 times as high, right? Vf squared is vi squared plus 2ad.
So John Michell was keep thinking,
you give the cannonball 4 times the velocity, it goes 8 times as high. 8 times the velocity, it goes 16 times as high, so on and so forth.
Then at what velocity? There would be some finite velocity. You can shoot the ball, so the ball never come back. And exactly Sir Isaac Newton equation gives us that number, 11 kilometer per second. If you shoot something with 11 kilometer per second at 90 degree, that ball will never come back because this will escape the earth.
So that's what Mitchell discovered from Newton's universal law of gravity.
It was known earlier, only a few decades before Mitchell did his work, by observing the period of the moons of Jupiter, that light actually had finite speed, which meant that if the escape velocity was high enough, Mitchell imagined, then wouldn't the escape velocity be so high that even light could not escape?
If you hit the escape velocity, then the cannonball would never return. Then Mitchell took this idea of escape velocity and applied it to the sun.
He looked at the sun and he realized that the
sun is a burning hot ball of gas, right? We can see the sun in the day sky every single day. Why can we see the sun? Because photons, light from the sun, escapes from the sun and reaches our eyes. What if you made the sun's mass so large, its radius so big, that the escape velocity of the sun was the speed of light?
Then the light will trap in the sun and they will never able to escape, and then nobody will notice the sun.
Then photons from the sun could no longer escape. We would not see the sun in the sky. It would become a dark star. A star that is so large that its escape velocity is the speed of light itself, and so even light itself cannot escape the star.
And thus, he figured out, or he hypothesized, the first instance of a black hole in literature, although the term black hole was actually not coined until all the way in 1965.
Now, more than 3 centuries after Sir Isaac Newton came another revolutionary physicist, Albert Einstein.
Einstein did his work in 1905, publishing his Annus Mirabilis papers, including one paper on special relativity. Following the postulate that the speed of light had to be the same in every single reference frame, he was able to devise a theory of motion that was vastly different from Newtonian mechanics in the way that it worked, yet reduced to Newtonian mechanics in the case of very low speeds. So, he published this work for the entire world to see, and later published the general theory of relativity, generalizing his previously limited theory to every single possible case. And this included a set of Einstein field equations. Einstein's field equations are very tricky to solve. Even today, finding solutions to them remains an open subject. But in the case of a very simple situation, you can actually find some very nice solutions to them. One of these very nice solutions was found all the way in 1917, only 2 years after Einstein published the general theory of relativity, by a brilliant technician
called Schwarzschild, found a simple solution to the field equation.
This German physicist simplified the Einstein field equations down to a scenario with exactly one mass, a single mass with uniform density that had no rotation. And so, this mass was spherical, which meant that finding the metric for it, according to Einstein's field equations, a mass was spherical and totally uniform in density, finding the metric was actually going to be quite easy. So he used this in order to devise a brilliant solution to the Einstein field equations. One that had two poles, one at 0 and the other at a Schwarzschild radius. Now, what were we solving for in the Einstein field equations anyway? We're solving for the curvature of spacetime, also known as the metric tensor. That's the variable. And what he found was that at two specific radii, r equals 0, the origin, and the event horizon, or the Schwarzschild radius, there were singularities in this curvature of spacetime. In other words, at this singularity, the curvature of spacetime was totally screwed up. It would just keep going in and in and in like the function 1 divided by x. And so that was the first case of a black hole being hypothesized. And that work was actually published on December 25th, forming a beautiful story.
What Carl Schwarzschild did to Einstein's field equations was very similar to what Mitchell did to Newton's universal law of gravitation. Carl Schwarzschild considered, what if you have a spherically symmetric body whose mass was so large, but whose radius was so small that its density was very large, and so its escape velocity was the speed of light. This was the Schwarzschild black hole, the simplest solution to Einstein's field equations.
Now, this isn't the whole story, actually. It took a very long time to deduce that black holes could exist in regular conditions, and then it took an even longer time until the work of Penrose and Stephen Hawking to deduce that black holes must have existed. And that all led up to the significant discovery we made in 2018, photographing the actual black hole Sagittarius A star.